The holographic universe theory is a compelling and widely discussed framework in theoretical physics that suggests our universe might function like a vast hologram. Proposed as a way to reconcile inconsistencies between quantum mechanics and general relativity, this theory posits that all the information that makes up what we perceive as a three-dimensional reality is actually stored on a two-dimensional boundary. This framework, if correct, could provide a profound understanding of the fundamental nature of space, time, and reality itself. Origins and theoretical basis. The holographic principle was initially suggested by physicist Gerard T. Hooft in the 1990s and later developed by Leonard Susskind. The principle drew on ideas from black hole thermodynamics, particularly Stephen Hawking's and Jacob Bekenstein's work, which showed that the entropy, or information content, of a black hole is proportional to its surface area rather than its volume. In simpler terms, this finding suggests that information about objects falling into a black hole is stored on its two-dimensional event horizon, rather than within the black hole itself. This insight led to the revolutionary idea that our three-dimensional universe could similarly be represented as a projection from a two-dimensional surface. How it works. The basics of holography. The holographic universe theory posits that just as a three-dimensional object can create a two-dimensional hologram, our 3D universe, with its spatial dimensions, could be a projection from a two-dimensional plane. This idea doesn't imply that the universe lacks three-dimensional qualities, rather, it suggests that the fundamental information about the universe could be encoded on a two-dimensional boundary, with our perception creating the experience of three dimensions. In practical terms, this concept proposes that all the information necessary to describe the universe exists on a surface, or boundary, and that everything we experience as three-dimensional objects and spaces emerges from this encoded information. Our perception of depth and volume might be an illusion, or a byproduct of the way we interpret the encoded data. Key implications of the holographic universe theory. 1. Resolving conflicts in physics. The holographic principle could bridge the gap between general relativity and quantum mechanics, two foundational yet often incompatible theories in physics. General relativity governs large-scale cosmic phenomena, while quantum mechanics explains subatomic behavior. The holographic principle introduces a framework that could unify these theories by suggesting that gravity itself may be a result of interactions on a lower dimensional plane. 2. The nature of black holes. Much of the holographic universe theory was inspired by the behavior of black holes. If black holes store information about everything that has fallen into them on their event horizons, then perhaps all objects in the universe do something similar. This could explain the long-debated black hole information paradox, which questions whether information that falls into a black hole is destroyed or preserved. The holographic principle posits that this information is not lost, but rather encoded on the event horizon. 3. Understanding quantum entanglement. Quantum entanglement, where particles separated by vast distances affect each other instantaneously, is a phenomenon that has puzzled scientists. The holographic universe theory could provide insight into this spooky action at a distance by suggesting that particles may be interconnected on a fundamental level through the two-dimensional plane, even if they appear separate in three dimensions. Mathematical model. Ante de Sitter, a conformal field theory, adds the CFT correspondence. In the late 1990s, physicist Juan Maldacena proposed a mathematical model known as the CFT correspondence, which is central to the holographic principle. This model describes a universe with negative curvature, like a saddle, and Ante de Sitter adds space, and correlates it with a quantum field theory without gravity, conformal field theory or CFT, on its boundary. Although our universe isn't an space, Maldacena's correspondence provides a theoretical basis for how higher-dimensional gravitational systems can be equivalent to lower-dimensional quantum systems. The CFT correspondence implies that gravitational theories in higher-dimensional spaces can be understood through quantum field theories in lower-dimensional, gravity-free spaces. This has led to the exploration of many potential applications of the holographic principle, including theoretical developments in quantum gravity and string theory. Experimental evidence and challenges. While the holographic principle is an elegant and mathematically supported theory, empirical evidence remains limited. Since we live in a universe that appears three-dimensional, directly testing a theory that posits a two-dimensional boundary is inherently challenging. Researchers, however, are exploring potential avenues. Cosmic observations. Some scientists are examining the cosmic microwave background, CMB, radiation for anomalies that could support holographic properties. Certain noise patterns in the CMB might point to holographic encoding. Particle physics and quantum computing. Advances in quantum computing and particle physics, such as the study of quantum entanglement and black hole thermodynamics, offer indirect methods of testing holographic principles. Simulation and data analysis. Recent work involves using computer simulations to observe whether phenomena observed in higher dimensions can be recreated through lower dimensional models, lending support to holographic hypotheses. Criticisms and alternative theories. While the holographic universe theory offers a fascinating perspective, it is not without its critics. Some argue that the theory is highly speculative and lacks direct evidence. Others contend that while mathematically sound, the holographic principle doesn't necessarily provide new predictions that can be tested experimentally, making it difficult to falsify or validate. Critics also point out that the ADS-CFT model, while robust in certain mathematical frameworks, may not directly apply to our universe's conditions, which do not exhibit negative curvature like ADS spaces. Current research and future directions. In recent years, research into the holographic principle has expanded, with applications in fields ranging from quantum gravity to condensed matter physics. Some researchers believe that understanding holography might even allow us to one day develop a complete theory of quantum gravity. Another direction involves the study of entropic gravity, where gravity emerges as an entropic force rather than a fundamental one, aligning with the holographic principle's implications. The holographic universe theory remains a tantalizing possibility that, if proven or better understood, could radically alter our understanding of space, time, and the very structure of reality. As technology advances, particularly in quantum computing and high-energy physics, we may come closer to validating or refuting this theory.